It's a very, very great pleasure for me to be here and for the National Science Foundation to partially sponsor this workshop. It's very important to bring people with different points of view together, with different perspectives on things. I know that my thinking, I've rewritten my talk in my mind 4 times since we got here this morning. It's all the interesting ideas that have come out. And thank you to the organizers for pulling together such a wonderful group of people here. I'm going to talk very little bit, about our future manufacturing initiative. It's the largest program we've ever had in manufacturing at the National Science Foundation. It's been in its 3rd year of execution, and we've spent somewhere in the range of $30 to $40 million each year in trying to encourage the academic community, university researchers, to come up with ideas that will define the future of where manufacturing is going. But I think that we're, or at least I'm somewhat disappointed in our vision of that future. I think in many ways manufacturing is stuck. It's stuck in slightly different ways worldwide. And we need a way out of that. And I think that it's not likely that the incremental progress that has been so successful in the physics-based modeling world will be applicable to that. We really need some new paradigm. And the best one we've got right now is machine learning. And the strength of machine learning is its ability to categorize experience. I'd like to just draw an analogy, and I'd like to try to keep it in your mind as I talk. And that analogy is to libraries. Libraries were very well organized. They had card catalogs that organized and a system, a repository, and standards, and all the things we've been talking about today. But as we all know, in the late 1990s, someone had a different idea about libraries, and it was that this new thing called the World Wide Web would be the library, and that what was needed was not a digital card catalog to organize all the old card catalogs so you could find your books using an ontology, but was needed was a new way of finding information in the library. And that was Google. And Google did not have a massive government program to set up a repository. It worked along with a very small set of simple tools in an established infrastructure that the government did establish. And those tools made it possible for people to do new things that they could never do before and that they wanted to do. And it made possible, it was so easy to use that 3rd graders could find what they needed in the library and could perform elaborate searches. And my guess is if we look at the future of manufacturing, it will have a lot more to do with developing a small set of simple tools that is useful in identifying the relevant experience in the library of manufacturing achievement, know-how, and experience, which is vast and excruciatingly detailed in its characterization of what we've done in the past and what we are doing now, than it is with having a complex structure of organized ontologies that organize everything to make it easy for people to do. And beyond that, I don't think it's very likely that most manufacturers are going to have the wherewithal to develop their own machine learning solutions to their problems. And I completely agree with Professor Marek that we're going to need a new kind of business, a business of system integrators that use these tools to employ the vast store of manufacturing knowledge and experience to slice that experience into narrow categories that are applicable to the individual problems of individual manufacturers. And that will be a business of paying for data, collecting data, dicing it into solutions, training models, and providing those models, selling those models to customers. So I want to talk a little bit about that. So a lot of this thinking came out of a series of workshops that NSF sponsored with the National Institute of Science, Standards and Technology. And it's been almost 2 years now. These workshops they're under the auspices of 2 subcommittees of the National Science and Technology Council in the United States. It's the government body that coordinates science policy across the government. The Subcommittee on Advanced Manufacturing and the Subcommittee for Artificial Intelligence and Machine Learning. This series of workshops brought together a very select cross-section of experts from industry, universities, and from government. These are not companies that happen to show up at the workshops. These were hand-picked representatives from organizations around the United States, and I think we got a very good coverage of expertise.
It's not functioning. I will do this instead of...
Oh, thank you. Next slide, please. One conclusion of this, there are many conclusions. I encourage you to take a look at these workshop reports. There are 3 reports. The report on the 3rd workshop should be out within the next month or so. It's just been distributed to the participants for comment. But one set of conclusions that we can make from these reports is that manufacturers right now want machine learning to meet them on their own terms. They're very interested in it. They want to accept it. They hope that it will help them to become more efficient. But they've got zero tolerance for letting their data out, just like everyone else. We've all got the same problem. Zero tolerance for letting their data out. And beyond that, they don't seem to really believe that there's enough benefit that will accrue to them from letting their data out. Oh, sorry. To make them willing to, or very interested in making that data available. They want machine learning methods that can be developed on the factory floor and implemented on the factory floor. You know, we kind of look at machine learning as one more tool to put in the toolbox and take down to the machine and install on the machine. But, you know, that's contradictory to all the experience in machine learning in every other industry in which it's applied. And I want to emphasize, there is no shortage of examples of industries that have been transformed by using this networked, data-intensive model industry-wide. It's almost every other industry except manufacturing. And we keep telling ourselves that it's because manufacturing is so different in so many ways that we can explain. But I really wonder if it is so different. I think more realistic will be that known machine learning methods will have limited application to manufacturing problems. And you probably noticed that most of the examples that have been cited so far in the workshop have used machine learning because, image recognition, because image recognition was the first application for which a method, successful machine learning method, was developed. Yes, there will be many applications in manufacturing where machine learning will be the method that's needed, but the other methods are essentially undeveloped. And in that regard, I think we're confusing 2 types of data in our discussions. One type of data is the data that's needed to develop the methods. That takes very extensive data and very high quality data. The good news is manufacturing companies are producing terabytes of that data every day. It's all labeled. It's all benchmarked against the quality of the items that are being produced. It's perfect for machine learning. But once the methods are developed, then they could be widely applied and widely used. So if you want to do machine learning for image recognition, you can access Amazon Web Services and have a very good solution, and you can employ that solution yourself. But again, if you've got an application that's not amenable to object recognition, you don't have a method. Somebody has to develop the method for you to use in your factory. That's going to require this data-intensive process, and we've not reached step one. We don't have the data sets available to do that method development. So that's the first job. Okay, this is probably very misleading, but it's my understanding of the history of machine learning. So, next slide, please. This is object recognition. So you can see that object recognition was 50% until about 2011. It wasn't very useful. It wasn't very much used. In 2012, actually, AlexNet was developed. What made that possible? A catalog of over 1 million labeled images was made publicly available so that machine learning researchers in the entire world could access this library of images and train machine learning systems. A competition was started, I think, in 2010 among all these different methods. These are the results: 50% success in the competition. That's the best algorithm. In 2012, AlexNet was developed. That was the birth of deep learning. That was the deep learning algorithm. It was much more successful in image recognition. Improvements on deep learning got us to the point we are today, where machine learning is pervasive for image recognition. It's a useful tool that can be used by anybody. Next slide, please. In the same way, the most recent breakthrough is protein folding. Protein folding problem has been solved using machine learning. This depended on an investment by the National Institutes of Health in the United States that started in the year 2000. National Institute of Health spent $500 million to determine crystallographically the crystal structures of proteins, folded proteins. In 2000 and next slide, please. That's 182,000 crystallographic determinations of protein structures. In 2018, there was another competition. In 2018, DeepMind developed the algorithm that was successful, the AlphaFold algorithm. Before AlphaFold, you couldn't do protein structure determination. It was very unreliable. Now in 2022, a method has been developed, but it took a $500 million investment to produce 182,000 known structures, and the resources and brilliance of AlphaMind to produce the algorithm made it possible. Now, AlphaFold is used routinely by chemists who want to determine protein structures. It's a tool that can be used, but it took a $500 million investment and 20 years to allow that algorithm to be developed so that it could be useful. Next slide. All right, so what's the path forward in manufacturing? And I want to emphasize it. If this is true, we've not reached step one. Step one is getting a data set that's useful in developing methods for manufacturing. Real machine learning researchers, they don't know what manufacturing is. They are plenty busy with problems that they know exist. On the other hand, I've had conversations with a few once they understand what manufacturing is, once they understand the amount of data that's available, once they understand the importance of the problems and the economic significance of those problems, they're very excited about working on manufacturing. And the next question is, where can I get some data to work with? And the answer is, there isn't any. There's no relevant data for what a machine learning expert wants to do. As I said, large manufacturers collect enough data every day to satisfy this need forever, but we can't get access to it. Why should a company make that data available? Well, from a selfish point of view, they can have the entire world research community working on solving their problem of their company. I would think that would be interesting to them, but it needs a much more effective presentation than this one. And, I think that's a wonderful problem for the international community to address. If we could get one great data set out of Europe and one great data set out of the United States and one great data set out of Asia, that would probably be enough to get these methods developed. There are also infrastructural needs. I don't know how it is in Europe, but in America, our industry doesn't have a workforce that can even collect data, that can instrument machines to gather data, much less analyze and process data or implement machine learning methods. We've got machines that don't have compatible sensors and data streams. They can't be aggregated. They need to be aggregated, but they can't be. We need machine builders, and they're already doing this, to produce machines with standardized suites of sensors and standardized signal formats so that all 10,000 machines in the world can have their data streams aggregated and categorized for machine learning purposes. We need methods to keep data sufficiently secure. And I put that in quotation marks because I think that's a moving target. Right now, data cannot be sufficiently secure to make manufacturers comfortable. There's nothing that will make them interested in sharing their data. I honestly think it's because why not protect data if it's useless, if it's not worth anything? It's not worth anything to them. It's not used by them for anything. Maybe if they could sell that data, it would be more interesting. Maybe if they believe that that data would provide them streamlined solutions that would make them much more competitive, it would be more interesting to them. But those are all barriers that need to be overcome. And then we need tools for categorizing and aggregating that data for manufacturing applications. And I think we can all agree that if we look far enough ahead in the future, if we look ahead 30 years in the future, that what we will have is a vibrant, networked marketplace, similar to the vibrant network marketplaces that we have for almost everything else these days, in which data will be collected, in which data will be aggregated and categorized and used to train a wide variety of models for different manufacturing applications. And there will be a service provider business that will sell those solutions back to the companies, and the machines will essentially set up themselves. That the machines will upload the parameters of the process, receive a model that has been selected from all similar processes worldwide, possibly. That model will be downloaded to the machine, and then locally that model will update in order to tune it for the specific parameters of the job at hand. So next slide. So is manufacturing all that different? At least at that level, it's not that different. It's pretty much the same as everything else. And next slide. I wanted to try and bring this a little bit down to earth because I know this sounds like crazy dreaming of some kind or not very realistic, but just notionally, how would this work? So here's an example in identifying suppliers. This is a huge problem in the United States and probably everywhere in the world. But say you're a small company and you're trying to get your product manufactured. How would you find the manufacturers to produce that product? It's almost impossible. You could call people, you could pay a consultant a few $1 million, you could do searches on the web or use the Thomas Register. But what most companies do is they get on an airplane and they go to Shenzhen. And in Shenzhen, they've got the manual version of this process. They'll sit down a number of manufacturers and they'll explain to you how to make your product and figure out how to make your product, and it'll solve the problem. But we'd like to have a better way to do that, and a better way that leverages domestic manufacturers. So let's say company A has CAD files for its parts B through N of its product, new product it wants to produce. And they want to produce it domestically. So many manufacturers in the United States have CAD models of parts they've made in the past that are similar to those parts. And every one of those CAD models has an exquisitely detailed geometrical representation. And let's say we had a tool that all of those CAD files were mounted up on the web in something that looks like a web page, and a web browser and a search engine had crawled through all those CAD files and categorized and indexed them so they could be easily searched. And that piece of software could go out on the web and find the CAD files that had similar geometries to the CAD files that are desired. Okay. So that search, that search page of possible matches has a company on it, company A, that's been identified as having made a very similar part to the part that's desired. And and of course, since manufacturer XXX has already manufactured that part, that manufacturer already has the machines and the tools and the setups and the process plans and the CNC code and all the specialized expertise that it took to get that part into production. So it's a perfect supplier for your part. Somebody who knows exactly how to make your part and has all the equipment you need to make it. So that should be a very low-cost part to the customer and a very high-profit part for the manufacturer. And, manufacturer XXX also has had a lot of experience in how to improve that part, so can probably give you a lot of suggestions about how to make your part better or improve the design. And therefore, you can use this search utility to identify all of the domestic manufacturers for all of the parts you need at low cost and high quality. So that would be very useful if we could do that. That's a potential machine learning problem. It's a problem. It's a geometrical problem, just like protein folding and image recognition. We should get some people working on that problem. What we need is a huge library of CAD models. That's difficult too, but why is that so impossible? Most CAD vendors have libraries on file of millions of CAD models that they keep proprietary to their customers. Isn't there some way we could anonymize those files or run these problems behind their firewalls? Or isn't there some way to make that work? We should find a way to make that work. Next slide. Here's the next level. So process control. So I'm producing that part. I want to have a process controller for that part. What I traditionally do is I get my experts and they come next to the machine and they set the parameters and they adjust the parameters and we test the quality and we eventually, within a few weeks or a few months, we figure out how to make that part successfully with high quality. But again, what if we start from the CAD models of all the parts that have been produced and web accessible? So now we can characterize the parts at least by geometry. All right. And let's say that manufacturer A wants to produce part B on a machine with a model number of XYZ. And there are many, many of these machines in the world, and they've all been producing parts of various types for a long, long time. And we have CAD models for all those parts. And let's say that service provider QQQ has trained a global machine learning-based process controlling controller using all the available data streams from all of the parts that have been produced on that machine that are similar to part B, and has trained a machine learning method to control that process using the sensor signals that are coming off the machine. And that allows manufacturing A to go to service provider QQQ and purchase that machine learning model. And it's downloaded to their version of the machine for their version of that part. And it's a model that can be used to control the manufacturing process for that part. And that would provide the beginning of a self-financing manufacturing service marketplace that could service manufacturers in the United States or worldwide. So again, a few, not simple tools, but the availability of a few tools with the right functionality could make machine learning a viable business that could finance its further growth through the profits produced from the savings of its customers. Okay, so next slide. There's plenty of opportunity for the research community worldwide. I think we could even attract machine learning researchers to this problem, maybe even DeepMind. I mean, that would be amazing. I was at a seminar recently by a machine learning researcher, and she said that they can't compete with DeepMind anymore. DeepMind's resources are so deep, academic researchers are having trouble keeping up. This kind of data-intensive business model has transformed almost every other major industry except for manufacturing. It's a very successful model. I mean, machine learning has squeezed the inefficiency out of everything else. The inefficiencies in manufacturing are enormous. I mean, every manufacturer is developing its own solutions for itself. Can you imagine the duplication of effort? I mean, imagine if you could go out and find the company that's already solved your problem and buy the solution instead of spending weeks and months solving every problem you've got. Manufacturing needs different tools, but the primary barrier to developing those tools is lack of access to the high-quality data that's needed to produce the methods. That data exists in quantity. If we could just find a way to convince the people who have it that it's to their benefit to do so. And in my mind, that makes the problem much more cultural than technical. The culture of manufacturing is opposite of the requirement for a vibrant machine learning infrastructure for manufacturing. And last slide. So that's a good opportunity for all of us. And in particular, I want to mention these two bilateral agreements. We've got a bilateral agreement with the Czech Science Foundation and a bilateral agreement with the DFG for joint projects between U.S. researchers and Czech researchers and U.S. researchers and German researchers. One proposal, it's considered by both science foundations. It's reviewed jointly by the two science foundations, and it's funded separately by the two science foundations. These would be wonderful projects. So I encourage all of you to think about this. I'd be happy to talk about it, and I encourage you to please let's get our resources together. We don't need, as I said, if we had a small handful of good data sets, we could probably change the world.